Now we're starting a new chapter called equilibrium. And for equilibrium, the best way to describe it is by looking at a video that I've attached to this lesson. Watch that video before you complete this video. So just shut this off, go back and check that video out because it's a really good representation of what equilibrium is all about. Okay? Do it now. Okay, so what we're going to do is we're going to look at how reactions work in equilibrium. And remember, just like any other reaction, as if it was one way, you're going to lose a certain amount of this and you're going to gain a certain amount of this. And if you recall from Chem 1, it was a matter of the coefficients for something that we call stoichiometry. Ooh, stop crying, but it's really not that bad. But we're going to use stoichiometry to figure out the changes. Now, the big difference here, as Mr. Anderson was talking about, is the fact that you actually have two reactions at once. You have N2O3 going to NO2 and NO, and then these are going to collide with each other and reform N2O3. It's going to be back and forth, and eventually reaches a point called equilibrium, where the rate forward and the rate backwards turns out to be the same. And then we'll get into the mathematics of all that in terms of how we can predict how that's going to work later on. But for right now, we're going to look at the fact that we're not going to get all 1.5 moles to break down into NO2 and NO. It's going to be a partial breakdown. Okay? Kind of like driving a Ford. So, what you're going to do is, we're starting with 1.5 moles in this is number 21. We have 1.5 moles of N2O3. And we have no moles of NO2 and no moles of NO. That's initially, so we're going to put an I there. That's the initial part before anything starts bumping into each other. Once they start bumping into each other, then these N2O3s are going to collide with each other and break down and form these two products over here. And then they're going to collide and reform the N2O3. And like I said, it's a back and forth thing. But one thing we do notice here is that we start off with nothing here and we end up with 0.45 here. So we're going to look at something called the change in quantities between the reactants and the products. So we gain 0.45 moles to get this. Now the stoichiometry here is a one-to-one relationship, so whatever we gain here, we're going to gain here. So we're going to add 0.45 moles here. So that's going to make that 0.45 moles at equilibrium. So we're going to put an E over here. Now here comes the kind of tricky part, but I think you can follow the logic fairly easily. Being the veteran chemist that you are at this point in your career, if we gain 0.45 here, what's going to happen over here? We're going to gain 0.45 here? No, that's called magic. Magic doesn't happen in chemistry. We're going to lose it, and that's going to donate it in this 1-to-1-to-1 stoichiometric ratio. So if we gain over here, we have to lose over here. This has to donate those 0.45 moles to breed those over there. And I'm saying, well, why does it split it in half? What should it be 0.225 and 0.225? Oh, may I say, because you have to follow the stoichiometry. 1-to-1-to-1 means the amount lost equals the amount gained equals the amount gained. Okay, remember the stoichiometry to this. So this is going to give us 1.05 moles. So at equilibrium, we're going to end up with 1.05 moles of N2O3, 0.45 moles of NO2, and 0.45 moles of NO. This is called an ice process. And we're going to be using ice throughout this chapter. This is the basic idea for it. Okay? So let's go on to number 23. Number 23, we have this reaction here. And we were given two reactants here and no products. But we're also told that when the reaction comes to equilibrium, we have 0.0389. So that must mean we gain 0.0389 here. Because I'm really good at math. Just because it's easy. All right, goes to zero. Ice, baby. Now we got to be careful of coefficients because we have a 2 here and we got a 2 here. Well, if you got a 2 here to 2 here, that's a 1-to-1 ratio between these two right here. Here's the arrow, which means you have positives on this side, negatives on this side. So for this NO, which has the same coefficient as this, it's going to lose the same amount, 0.0389. However, the amount that this is going to lose is not going to be the same as this because the coefficients are 1 to 2. So that means this is half of this. So this is actually going to be minus 1/2 of 0.0389. And we do the math here, that turns out to be 0.0195. Well, we can cross it out and put minus 0.0195. Okay? So, now I subtract this and I'm going to get 0.0266 moles. And this is going to give me 0.0133 moles. So at equilibrium, I'm going to have a mixture of these three quantities within my beaker where this reaction was run. Very simple math, but you know, this is probably the challenging part right here. Look out for the coefficients and follow the pattern with those numbers. Number 25. We have a synthesis of methanol, although it's gaseous instead of liquid, so this is obviously a high temperature reaction. Well, we start with these two reactants, and you see that we start with 0.1500 here, and we ended up with 0.1187. So that means that we've lost when you subtract these two right here, then you're going to get 0.0313 moles. That's going to give us that value right there. So we have to subtract this from this to figure out what the change was. Change, you say? I say yes, because it's ice. Cool, huh? Okay. Now, because we have 0.0313 here, and look, we got a 2 here as opposed to a 1 here, so instead of losing 0.0313, it's going to lose twice as much as this loss over here. So this will be minus 0.0626 moles, which at equilibrium is going to become 0.2374 moles. And over here, it's going to gain the same quantity as this right here because they have the same coefficient, 1. We're number 1, getting this done right. So this is going to add 0.0313 mole to give us, sure enough, 0.0313 mole. So the equilibrium mixture in our beaker, whatever amount of time it takes to get to that point, is going to have this mixture of these three quantities. And that is reaction stoichiometry. Your assignment. It's going to be page 683, I think is what it says. Whatever this back up. Oh, 684. Of course, page 684. Problems 22 through 26 here. Have fun.